One of the hottest areas for the development in the nanofiber technology is, in fact, tissue engineering. In fact, there was a report produced by Thomson Reuters on the hottest topics in material science in 2011. And number 7 on this list was tissue engineering using nanofibrous materials. The beauty of this application is that the nanofibers very nicely mimic the extracellular matrix material produced naturally by the cells in the body. So when cells grow and produce extracellular matrix, this is a fibrous collagen matrix material. And when you look at the collagen, the size of the fibers, the porosity of the material, the elasticity of the material is very much in the same range of sizes and material properties as what we can produce with electrospinning with this nanofiber technology. And so this has been recognized. Now, tissue engineering is a very challenging field and very early in its development. So I can't say, how far commercialized tissue engineering is, but on the academic side, it's probably the hottest topic in nanofiber technology because it's such a natural fit. We were funded by the U.S. Army to produce a type of membrane that would provide more protection to the soldier or first responder who might be exposed to industrial gases or chemical warfare gases or aerosolized warfare agents. So one of the natural properties of these materials as membranes is they're very porous, so they're breathable, so they allow vapor to pass through them, but they will filter out most aerosols. And because of their high surface area, they can be decorated with specific chemistries that will react with bad-acting warfare agents or industrial gases. And so we developed a material that could be used as part of a uniform or a chemical protection suit that had the features that it was breathable because it allowed vapors to pass through so the body could cool itself, but at the same time was waterproof, filtered out any external aerosolized species, and would react with typical nerve agents that someone might be exposed to. So we produced actual samples of these, and they went down the street and were tested at the Army lab at the Natick Soldier Research and Engineering Development Center, which is in Natick, Massachusetts. So another application we've been looking at is to perform separations where the fibers are designed so that they actually are electively conducting, and we can make an electrode material out of them. They're basically carbon fibers. But we can decorate those carbon fibers with some kind of functional material. One, for example, that we've used is a redox material, which means that when you pass current through the electrode, the material that's on the surface will either expand or contract. And when it expands and contracts, it can exhibit a different affinity or likelihood to absorb, let's say, an organic material out of an aqueous solution. So now you have another way of separating oil and water by passing a current through the fiber, which is decorated with this redox active surface species, surface functional group. It will become oil loving and absorb the oil species from the stream until it's fully loaded and reaches its capacity, and then you have to regenerate the material by passing a cleaning stream across it. Then you reverse the current, the surface functional groups expand, and they release the organics that they had absorbed in the previous cycle.